In this tutorial, we will be discussing the concept of rate orders for reactants and chemical changes in a more formal way. As was demonstrated in the previous tutorial, to determine the effects of changes in concentration of a particular reactant on the rate of a reaction, experiments are performed using different concentrations of it and observations are made. As can be recalled, the rate of a reaction can be measured either by a change in concentration of a reactant or product that is measurable. For example, in the reaction between hydrochloric acid and sodium thiosulfate, the rate at which sulfur is formed was used to measure its rate. The graph above shows how the concentrations of reactant A and product B change with time. Recall that in one of our previous tutorials, we showed by calculation how the rate of a reaction slows down with time using a product to measure its rate. So if the average rates are calculated for segments 1 and 2 above, it will be found that the value for segment 1 is greater than that for segment 2. So that shows that as time goes by, the rate of a reaction decreases. So neither of these two values could give an accurate representation of the rate of the reaction. The one that will give the most representative value for the rate of the reaction is the slope to the tangent x found at the very beginning of the reaction. And this is called the initial rate of the reaction, and it is calculated by using the initial concentration of either a product or a reactant. The graph besides shows how the concentration of reactant A changes when 4 experiments are performed using different concentrations of it. These are illustrated by the blue lines. The red lines represent the tangent that are used to calculate the initial rates for the reactions. Notice how when the initial concentration is low, the initial rate is also low, and when the initial concentration is high, the initial rate is also high. So based on the observation above, the relationship between the initial rate of a reaction and the initial concentration of reactant A, the rate of the reaction written as rate is equal to a constant times the concentration of that reactant, where K is called the rate constant of the reaction. Now listen to this. If a reaction has only one reactant, say A, and change in concentration of it changes its initial rate, its rate is written as rate is equal to K into the concentration of what is. If a reaction has two reactants, A and B, and changes in concentration of both change their initial rates, then the rate is written as rate is equal to K times the product of the concentrations of A and B. If a reaction has 3 reactants, A, B, and C, and changes in concentration of all 3 change their initial rates, then the rate is written as K times concentration of A times the concentration of B times the concentration of C. And this brings us to what is called the rate law equation. If a reaction has a number of reactants and changes in concentrations are made for each one separately, the rate of the reaction may change differently for each. The way the rate of the reaction changes is related to what is called the rate order of the reactants. Their rates will be proportional to the product of their initial concentrations raised to some particular exponential powers. Rewriting the above equation using letters of the alphabet to represent these exponents, we have the following rate law equation for the reaction. So if you rewrite this equation here, and using these letters of the alphabet that are called rate orders, this is the rate law equation. So it will be equal to k times a to an exponent x times concentration of b to an exponent y times the concentration of c to an exponent z. And one could have used any letters of the alphabet to represent those exponents. And these here are called rate orders of the reactants A, B, and C respectively. Now listen to this. These values here must be determined experimentally. The following are examples of experiments that have been carried out that determine the values of the rate orders of reactants and their rate law equations. The following table gives the result of the rate of production of a compound X at a particular temperature when the concentrations of the reactants given by the equations are changed as shown in the table. So this represents the chemical reaction that's happening. Reactant A is reacting with B and C to give you a product X. And like we said before, you can use either a product or a reactant to measure the initial rate of change of the reaction. In this case, they're using product X. And that is what you're going to see in this table here. You're going to see initial rate of production of X. Like we said before, it is only the initial rate that is representative of the real rate of the reaction. So we have 3 reactants, and a number of trials must be carried out to show how each one of them, if it is changed separately, affects the rate of the reaction. So in this column here are the initial concentrations of reactant A, that for B, and that for C. Let us see what happens in the first trial when that concentration of A was used and mixed with these concentrations of B and C. So these were the initial concentrations of reactants A, B, and C. And the rate of the reaction was found to be 4.0 times 10 to the negative 4 mole per liter per second of formation of X. Now this is the deal. In doing these trials, only one variable is changed at a time. So if you look at the second trial now, you can see that this concentration stayed the same, that one stayed the same, but this one here is doubled. So they wanted to see how the change in concentration of A affected the rate of the reaction. So in trying to find the rate order of any reactant, this is what we do. We look at a trial in which the concentration of one of the reactants has been changed, and you can see it is changed for reactant A in trial 2. So the next thing that we have to do is to find out how A affects the rate of a reaction, and in so doing, that will allow us to calculate the rate order of A. Next, express the rate law equation as k times x to the exponent x times b to the exponent y and c to the exponent z. So now you want to see how A affects the rate. Go to the table. I always tell my students to avoid working with fractions and decimals. Divide the values in the trial that has a higher concentration by the one that has the lower concentration. So in this case, we'll take all the values for trial 2 and divide them by all the values for trial 1. Take rate 2, divide by rate 1, put in all the values for rate 2 here in terms of concentration. This is the concentration of A in rate 2, B, C, and these are the concentration of A, B, and C in trial 1. You take rate 2 value here and you divide that by rate 1 value here. Of course, these are raised to the exponents x, y, and z. You can see all of these here will cancel out. These will cancel out here. But you're going to have 2 to the exponent x, and that works out to give you 1. But listen to this. Any quantity raised to an exponent that gives an answer 1 is 0. So in this case, x will equal to 0. Note that, eh? Anytime you have 2 to the x or 4 to the x and you ended up with a value of 1, it means that the exponent there is 0. So what do we write? We will say, therefore, the rate is proportional to the concentration of A to the 0 power. What does that mean? Any increase or decrease in the concentration of A does not alter the rate of the reaction in any way. Okay, so we know that A has a rate order of 0. Now we want to see how B affects the rate. So we go back to this, we observe now, this is where B has been changed. These two here remain the same. Okay, which trial do you think we should divide by which trial? To avoid using fractions and decimals, divide all the values in trial 3 by those of trial 1. That's the rate in trial 3. That's the rate in trial 1. These cancel out here. These cancel out here. That goes into that 2. That goes into that 4 times there. So we can say that y is equal to 2. These represent the concentrations of B raised to the power y. So the rate is proportional to the concentration of B raised to exponent 2. So the rate order of B is 2. What does that mean? Doubling the concentration of B quadruples the rate of the reaction. Now you want to see how C affects the rate. You go to the table now. Everything stays the same here, stays the same here as there. You only change this one variable here. So what trial should be divided by what trial? We'll take the values of all of these here for trial 4 and divide it by the values of those there for trial 1. So doing that, we get all of these here will cancel out, cancel out. You will get a value of 2 here. That goes in that twice there. 2 to the z is equal to 2. So z must be equal to 1. We see that the rate of the reaction is proportional to the concentration of C raised to the power of 1 or exponent 1. So we have 3 rate orders. One was 0, one was 2, and this one is 1. So what do? We now substitute 0 for the rate order of A, 2 for the rate order of B, and 1 for the rate order of Z in the rate law equation. So this is going to become 0 there, this is 2, and that is 1. But note something now, look. If a reactant has a rate order of 0, it is not included in the rate law equation. Okay? So rewriting this equation, we get that rate is equal to K times B to the exponent 2, C to the exponent 1. When you don't see the 1 there, it is assumed that it's equal to 1. So the overall rate order for this reaction will be the sum of the rate orders for the respective reactant in the equation. And now we go on to calculating what is called the rate constant K. We know that rate is equal to K times the concentrations of B to the exponent 2, C to the exponent 1, just doing that for convenience there. Therefore, to find what K is, we'll take the rate and divide it by this expression here. Take any rate. So this is the deal here, that's it. Now we're using values from trial 1. Let's go to the table now and see what these values are. This is the rate here. The rate will be equal to 4.0 times 10 to the negative 4 moles per liter per second. And the concentrations will be that for A, that for B, and that for C. You can't use this rate here and use these values here, okay? Whatever rate you choose, use the values of the reactants that are used to produce that rate. So we go back now. Rate constant will be equal to this here, divided by this value for B. This is the value for B raised to this exponent, and that's the value for C raised to exponent 1. We don't put that here. But I want to show you something. There is a principle in mathematics that says if you have A divided by B divided by C, it's same as taking A and you multiply by C divided by B. So that's what we'll do here. We're dividing by liter per second here. It now becomes this here multiplied by second divided by liter times liter to the third power divided by 0.1 mole to the third power. If you do the math, you're going to get this. Well, look at the units. You have 1 mole here, but you have 3 at the bottom here. So you become mole to the negative 2. Liter, you have 3 at the top there, but you only divide by 1. So you become square, and second stays the same. Let's look at another problem again. Hopefully by doing these examples, you'll get a good understanding of how to find the rate orders and the rate law equation and how to calculate the rate constant. In this reaction here, D is reacting with E and F to give you X and Y, but apparently Y is a measurable guy, so they'll use that to calculate the rate of the reaction in all these different trials here. So in the first trial, you can see these are the concentrations here. The rate of the reaction is 5.0 times 10 to the negative 4 mole per liter per second of Y formation. Which one has changed? This one has been changed. Only rest here stays the same. And this is the rate of the reaction. Sometimes, you see how that has a negative 3? I make it easy for them to see. Look, this is same as 20 times 10 to the negative 4. Everything stays the same here, stays the same here. All you have to do is to divide that by the 5 there. So go 4 times inside. Just to show you an alternative way of making life easy for you if math gives you a problem as it does to me. We will divide all the values in trial 2 by all the values in trial 1, and you will see how D affects the rate of the reaction. These will cancel out, they're the same. This is to the x power here. So 2 that goes into that 2 to the x is equal to 4. So x must be equal to 2. 2 times 2 equals 4. Therefore, the rate is proportional to D to the exponent 2. What does that mean? Every time you double the concentration of D, the rate of the reaction quadruples. Next, we want to see how E affects the rate. Let's go, check table out. E is changed here. This stays the same as that. This is the same as that. Okay, so what do we divide? We divide all the values in trial 3 by all the values in trial 1. And let's see what we have. These cancel out. These cancel out. This goes 2 to the y. And when you do this division here, you get 1. So what do you think happens? Y will be equal to 0. Okay? Again, making this point for you to know, anything raised to some exponent that is equal to 1, the exponent must be equal to 0. So in this case, y is 0. Okay? So rate is proportional to E to an exponent 0. Any decrease or increase will not affect the rate of the reaction. You want to see how F affects the rate of the reaction. Go to the table. There's a slight deviation here. I want you to pay attention to that. They may give you something to just to catch you. Okay, F has not been changed except in this trial here. But look, they give you a curveball here by changing the concentration of D. So we cannot divide trial 4 by trial 1. We have to divide trial 4 by 1 where you have a change here, but there is no other change in these here. And it corresponds to trial 2. See the value here is same as the value here, and the value here is equal to that. So look out for those subtle changes, okay? So what are we going to do? Divide all the values for trial 4 by the values for trial 2. 2 to the z is equal to 2, so z is equal to 1. we see that R is proportional to the concentration of F raised to exponent 1. So substituting the rate orders of 0 for E, 2 for D, and 1 for F in the rate law equation, we get that rate is equal to K times D to the exponent 2, E to the exponent 0, F to 1. And of course, we will not include that in the equation because it has a rate order of 0. So this is a final rate law equation, okay? The overall rate again will be equal to the sum of those exponents there for the entire reaction, which will be 3. Calculating rate constant following the same pattern again, we'll take any rate and divide it by the concentrations of the reactants raised to those exponents in that rate. So we're going to take value for trial 1, take that rate there, divide by these. This is the same as this, and now it's same as if we take this value here and we multiply by second over liter times liter cube at the top there, divide by that value there, and when you do that, you'll end up at that value there for the rate constant with those units there. In this third example, solutions of hydrogen peroxide, iodide ions, and an acid are reacting to produce water and iodide ions with a 3 negative charge. A series of experiments were performed at a certain temperature using different concentrations of the reactants. The initial rates of production of I3 negative ions for each experiment was determined as shown in the table below. We are not asked to use the data provided to derive the rate law equation and to calculate the rate constant for the reaction. So we shall inspect the table to see how the concentrations of each of the reactants was changed and what rates were produced. Starting with hydrogen peroxide, we can see that in trial 2, its concentration was doubled. All the others remained the same, and that was the rate given. So to find out how the change in the concentration of hydrogen peroxide affected the rate of the reaction, what trial do you think we should divide by what trial? Again, we'll take the one that has the higher concentration, divide by the one that is having a lower concentration. So we take all the values in trial 2 and divide them by the values of trial 1. But before we do that, we have to express the hypothetical rate law equation for the reaction. And we say is equal to K times hydrogen peroxide to the exponent X, iodide ion to the exponent Y, and hydrogen ion to the exponent Z. Dividing values of trial 2 by those of trial 1, we have these. These will cancel out. All these will cancel out here. These will cancel out. Cancel out. Dividing the rates, we get a value of 2 here. Here, doing the math, we get a 2 to the exponent X is equal to 2. And therefore, X is equal to 1. We can therefore say that the rate of the reaction is proportional to the concentration of hydrogen peroxide raised to an exponent 1. For convenience, you can do that. Normally, you don't do that. It is understood when everybody see it like that. Next, we want to see how a change in concentration of iodide ions affected the rate. We go to the table, see where the concentration of iodide ions have been changed, and the rest remain the same. We can see it has been changed in the third trial. These remain the same here, and that's the rate there. So what trial should we divide by what trial? We should take all the values of trial 3 and divide them by the values for trial 1 to see how the change in concentration of iodide ions affected the rate of the reaction. So doing that, we get these expressions here. These will cancel out. These here will cancel out. And this works out to be equal to 2 to the y exponent. Divide the rates, we get 2. So we can say that y is equal to 1. Therefore, we can say that the rate is proportional to the concentration of iodide ion to the exponent 1. Finally, we want to see how a change in concentration of H affected the rate. We go back to the table and inspect it to see where hydrogen ion concentration has been changed. We can see it has been changed here. Nothing else has been changed. Let's stay the same. Let's stay the same. Let's stay the same. So what trial do you think we should divide by what trial? We should take all the values of trial 4 and divide them by the values of trial 1 to see how a change in concentration of hydrogen ions affected the rate of the reaction. So doing that, we have these expressions that will cancel out, that will cancel out, cancel. But of course, all of these here are expressed to the exponent z. Doing the math there, 2 to the z exponent is equal to 1. And again, we know that z is going to become 0 because we say any quantity expressed to an exponent that gives an answer 1, then this exponent is equal to 0. What does that tell you? That any increase or decrease in hydrogen ion concentration would not alter the rate of the reaction anyway. So we say that the rate of the reaction is proportional to the concentration of hydrogen ions raised to the exponent 0. Finally, we will substitute the rate order 1 for this, 1 for iodide and 0 for hydrogen in the rate law equation. So making that 1, and of course we're not going to put in hydrogen there because it has a rate order of 0. The overall rate order for the reaction is equal to the sum of the rate orders of each of these, and that's equal to 1 plus 1, and that'll give you to 2. Isn't that a little quiz here? What will be the rate of reaction if solutions containing the following species are mixed with those concentrations there? We have that for hydrogen peroxide, that for iodide ions, and that for hydrogen ions. Why don't we go to the table and see where we have that for hydrogen peroxide, that for iodide ions, and that for hydrogen ions, and see how the rate will differ. So we have that for hydrogen peroxide, that for iodide ions, and we have that for hydrogen. Note that hydrogen does not affect the rate of the reaction. Note that the rate will be determined by the concentrations of these two other reagents, and it should be that. Calculating the rate constant. Again, we say that the rate constant is found by taking any rate and dividing it by the concentrations of these here where that rate was formed. Using the values from trial 1, we get that the rate constant will be equal to that. Let's check it out. Yes, that's what it is there. Divided by that for hydrogen peroxide and that for iodide ions, which is this. Divided by that, which is this. We're just expressing this in a different way to show you how this is at the bottom here. And doing this in a mathematical way that will help you to derive the correct units for the rate constant. So now we do an inversion here, and we do it for this too. The square goes to the top and this comes to the bottom here. And when you do your calculation, it turns out to be that because you have 1 mole here and 2 moles at the bottom, you're going to end up with a negative 1. Liters, you have 2 at the top there, 1 at the bottom there, you're going to positive 1, and of course second will stay at the top there. So that's the value for the rate constant. Next question is, what will happen with the rate constant if the temperature of the reaction is raised? Of course, raising the temperature of a reaction causes the rate of the reaction to increase. So this value here is going to go up a little bit more, but the units will stay the same. So they're giving you a scenario here. This is the reaction. A reacting B plus C to give you D and E. They're monitoring the rate of reaction by which E is being produced. See what they're asking you, what I'm asking you. So this is the rate law equation that has been derived. What can be deduced from that? C is not being featured here. That means that C has a rate order of 0. So increasing the concentration of C does not affect the rate of reaction. Doubling the concentration of A because it has a 1 there will double the rate of the reaction. However, doubling the concentration of B because it has a rate order of 2 would quadruple the rate of the reaction.